Okay, let's unpack this. Think about just your regular day.
Mm-hmm.
You're searching for an email, right?
Mm-hmm.
Or maybe a file somewhere on your hard drive, looking up some info online.
Happens all the time. Finding your keys even.
Exactly. That basic task, finding one specific thing and, a whole bunch of stuff, it's everywhere.
It really is. And, we do it without thinking most of the time, but how you search, especially with like tons of data, that makes a huge difference.
Yeah, it's the difference between clicking and getting the answer.
Instantly.
Or sitting there watching the little wheel spin.
Waiting and waiting.
Yeah. And that's really what search algorithms are all about, isn't it?
Yeah.
So today we're doing a deep dive, really revisiting this, using some great material from Hello Algo. They lay it out so systematically.
They really do.
Our mission today isn't just to, list off names. We want to dig in properly, understand the core ideas, how they actually work, and, maybe most importantly, figure out when to use which one and why.
Right. The goal is for you listening to walk away with a really solid mental model, like a toolbox in your head for finding things efficiently, whether that's computer data or just thinking about how to tackle finding something in the real world. We want the stuff to stick with you, for the long haul.
Okay, and this is where it gets really interesting right away. The source material, it splits search approaches into two main camps. It's a really fundamental division.
It is. But maybe first, let's just quickly define what we mean by searching, like algorithmically speaking.
Good idea. Lay the groundwork.
So basically, a search algorithm is just a method, a recipe if you like, for finding one or more items that match some criteria within a data structure.
Data structure meaning things like...
Arrays, lists, trees, graphs. The ways we organize data, you've got this collection, and you need to pinpoint the things inside it that fit what you're looking for.
Got it. Find the matching items in the collection. And those two big categories the source mentioned.
Yeah, the first one is pretty straightforward. It's locating what you want by simply traversing the data structure.
Traversing. So just going through it.
Piece by piece, yep. Basically checking everything.
Like literally looking in every single drawer until you find that one sock you need.
Exactly like that. You're just exploring the whole space. The second category, though, is a bit more, let's say, strategic.
Okay.
It uses the way the data is already organized or maybe some existing properties of the data to find things way more efficiently.
Okay. So back to the sock drawer. If your socks are, perfectly sorted by color and type,
right,
you don't check every sock. You go straight to the Argyle section, maybe. You use the organization.
That's the core idea. One is brute force, just look everywhere. The other uses some kind of intelligence, some structure.
Let's dive into that first one then. Brute force search. The check everything method. Tell us about that.
So conceptually, this is the simplest approach. It just means you systematically visit or traverse every single element in whatever data structure you have.
One by one.
One by one. You check each one. Is this what I'm looking for? And you keep going until you either find it or you've checked absolutely everything and can say, nope, it's not here.
Makes sense.
Yeah.
Simple enough. And the source gives a couple of classic examples, right?
It does. The most basic one is linear search. You use this for simple linear structures like arrays or linked lists.
Just a line of items.
Exactly. You start at one end, check the first item, then the second, then the third, until you either find your target or you run out of items.
Standard procedure. Just scanning along. What if the data isn't just a simple line? What about networks or family trees, that kind of thing?
Right. For more complex structures like graphs and trees, the brute force methods are usually breadth first search, BFS, and depth first search, DFS.
Okay, BFS and DFS. How do they work?
BFS explores sort of layer by layer. Imagine starting at one point. You first visit all its immediate neighbors.
Okay.
Then you visit all their neighbors that you haven't seen yet, and so on. It spreads outwards like ripples, near to far.
Okay. Like exploring all the rooms on the first floor of a house before you even think about going upstairs.
That's a great analogy. Yep. And depth first search, DFS, is different. It goes deep. It follows one path as far down as it possibly can.
Like going down one branch of a tree.
Exactly. All the way to a leaf node, perhaps. Then, only when it hits a dead end or finds what it's looking for, it backtracks and tries another path from the last junction.
Got it. So BFS goes wide first, DFS goes deep first. Now, brute force, I mean, the name itself sounds kind of clumsy, inefficient.
It can be, yeah.
Is there any advantage to this check everything approach?
There is, actually, and it's important. The source points this out clearly. The big advantage is simplicity and versatility.
Okay.
It's generally easy to understand, easy to code up. And here's the kicker. It needs zero data pre-processing,
Meaning?
meaning the data doesn't have to be sorted beforehand. It doesn't need to be in any special kind of structure. You don't need any helper tables or anything. You just take the raw data as it is, and you can start searching immediately.
Okay, that's a real plus. No setup required. Just point it at the data and go. But I'm guessing the downside comes when the data set is big.
That's exactly it. The major drawback is the time complexity. For these brute force methods, it's typically O-NALEM,
Big O of N, meaning
meaning the time it takes to find something grows, on average, directly in proportion to the size of the data. So if you double the amount of data,
search time roughly doubles.
yep, which might be totally fine if you only have, say, 100 items. But if you have millions or billions, linear search becomes painfully slow. Impractical, really.
Right, that linear scaling is the enemy when things get large.
Yeah.
Okay, so if the brute force story, let's talk about the second category, adaptive search, the smart ways.
Right. These are the methods that are specifically designed to leverage certain properties of the data or maybe use extra data structures to get much, much faster search times. They kind of adapt to the data's nature or how it's organized.
This sounds like where the real speed gains are.
Yeah.
What are the key examples the source talks about here?
Well, a classic one, especially for ordered data, is binary search.
Ah, yes, binary search. Heard of that one.
It works brilliantly, but only on sorted arrays, typically. Because it's sorted, you can jump right to the middle element.
Okay.
You compare your target to that middle element. If your target is smaller, you instantly know it must be in the left half right.
Right, because everything to the right is bigger.
Exactly. And if your target's larger, you know it must be in the right half. So in one comparison, you've just eliminated half the data.
Wow.
And then you just repeat the process on the half that's left. Check the middle, eliminate half again, check the middle.
Keep cutting the problem in half. That sounds way faster than checking one by one.
Oh, it's exponentially faster.
Yeah.
Then you've got hash search. This uses a completely different idea involving a hash table.
Hash tables.
Yeah.
Key value lookups.
Precisely. You use something called a hash function to calculate directly from the item you're looking for, the key, an index or a location in memory where that item should be stored.
So it tells you exactly where to look.
Ideally, yes. It gives you a near-instant lookup on average. It's like instead of browsing library shelves, the hash function calculates the exact shelf and spot for your book title.
Okay, that sounds incredibly fast, too.
Oh.
What else? You mentioned tree search.
Yes, tree search. This applies when your data is organized in specific tree structures built for searching, like a binary search tree, BST.
How does that help?
In a BST, there's a rule. For any node in the tree, everything in its left child subtree is smaller than the node's value, and everything in the right child subtree is larger.
Oh, okay. An ordering rule.
Exactly. So when you search, you start at the root, compare your target, and then you either go left if it's smaller or right if it's bigger. Yeah, you keep doing that down the tree, and each step potentially prunes away a whole huge chunk of the data.
So again, narrowing it down really quickly. Okay, the big appeal here is obviously speed. Much better than Broad. Yeah. What kind of performance are we actually talking about?
The source confirms, yeah, high efficiency is the name of the game. For binary search, and also for tree search, if the tree is reasonably balanced, you can get OGOG time complexity.
Logog. How much better is that than OD?
Dramatically better. Think about it. If you double the data size, time doubles.
Right.
But time barely increases. It just adds one extra step of comparison, essentially. It scales incredibly well.
Oh, okay.
And then there's hash search. On average, its time complexity is O1, constant time, meaning it takes the same amount of time regardless of whether you have 10 items or 10 billion.
On average, yes. That's the ideal. It sounds almost too good to be true, right?
It sounds like magic. Why would anyone ever use anything else if you can get O1 search? There must be a catch.
Oh, there definitely is. The source is very clear about this. All this speed, it comes at a price. These adaptive methods, they often need data pre-processing.
Like what?
Well, for binary search, the data absolutely must be sorted first. And sorting itself takes time. Good sorting algorithms are usually, okay, so you have to spend time sorting before you can even start the fast search.
Right. And for hash search and tree search, you need to actually build those extra data structures, the hash table or the tree. That also takes time, usually for hashing and maybe building a balanced tree. And crucially, these structures require extra memory space, too.
Extra space.
Yeah, the hash table itself takes up memory. The nodes of the tree take up memory, separate from just storing the original data items.
Okay, so you're trading. You invest time up front for pre-processing, And you invest extra memory for the structure.
In order to get that faster search speed later, it's like building a super organized filing system. Takes time and space for the cabinets and folders, but then finding a specific file is quick.
Makes sense. And what if the data changes a lot? Adding things, removing things.
That's another part of the cost. Maintaining these ordered structures, keeping the array sorted for binary search, keeping the tree balanced, handling hash table resizing adds overhead. It takes more time and effort to insert or delete elements compared to just, say, sticking a new item at the end of a simple list used in linear search.
Right.
In fact, the source notes that often when people just talk about search algorithms, especially in contexts like databases or system design, they're usually referring to these adaptive ones because they're the go-to when fast retrieval is a primary goal.
That tracks. They're the performance players.
Yeah.
Okay, so we've got the two families. Brute force, check everything. Simple, no setup, but adaptive, use structure. Fast, but needs setup and maybe extra space. We've seen examples like linear, binary, hash, and tree search.
And we've seen the core trade-off emerging. Simplicity versus speed, setup cost versus query speed, space versus time.
Which brings us right to the critical question. How do you choose? Which tool do you pull out of the toolbox for a given job?
Exactly. Knowing they exist is step one. Picking the right one is step two. And it really depends on the specifics of your situation.
The source actually provides a really neat comparison table, doesn't it? Lays out linear, binary, tree, and hash search side by side.
Yeah, it's super helpful. It compares them on several key metrics. Performance for different operations, space requirements, setup needed.
Let's walk through that. First, the obvious one, searching performance. We've kind of covered this, but let's recap the table's view.
Okay. Linear search, binary search, tree search, assuming it's balanced. Also air search, on average.
Clear differences there. Okay, what about inserting a new item? How do they stack up?
This is where it gets interesting. Linear search, if you can just add to the end of a list or array, that's often very fast. Hash search is also typically on average for insertion.
Okay.
But binary search requires a sorted array. Inserting into the middle of a sorted array means you might have to shift potentially half the elements over to make space. That's an operation. Slow.
Whoa. So lightning fast search, but potentially really slow inserts for a binary search in an array.
Exactly. It perfectly shows the trade-off. The structure that makes search fast, the sorted contiguous array, makes insertions costly because you have to maintain that structure.
Okay. What about tree search insertion?
For a balanced tree, inserting involves finding the right spot and then potentially doing some rotations to rebalance, and it averages out to still efficient.
Fascinating. How about deleting an element? Similar story.
Pretty similar pattern, yeah.
Right.
Linear search needs usually, because first you have to find the element, which is a place, and then maybe shift elements if it's an array. Binary search on an array, again, finding is shifting, but deleting and shifting is still slow for updates and arrays.
Yep. Tree search deletion in a balanced tree is also on average, and hash search deletion is, again, on average. Find the spot via hash, remove it. Okay, so summarizing updates, insert delete. Hash is generally fastest. Average, linear can be fast for appending, but slow otherwise. Tree is quite balanced. Binary search on arrays is terrible for updates.
That's a good summary of the table's implications there.
What about extra space needed? Memory cost.
Right. Linear search and binary search, when done on an array, are very space efficient. They work directly on the data. So extra space just needs a few variables for indexes and such.
Minimal overhead.
But tree search and hash search need to build their own structures. The tree needs memory for all its nodes and pointers. The hash table needs memory for its underlying array or list of buckets. That typically requires extra space proportional to the number of items.
Okay, that's the memory penalty for their speed, especially for hash and tree. Next up, data preprocessing, the setup work.
Linear search needs none. Zero setup. Binary search absolutely requires the data to be sorted first, which usually takes ON time.
That's a significant upfront cost if N is large.
It is. Tree search requires building the tree structure. For a balanced tree, that's also typically ON log N. Hash search requires building the hash table, which usually takes time you hash every element and place it in the table.
So more upfront work for binary and tree than for hash, but all adaptive methods need some setup compared to linear, and this preprocessing time is crucial, right?
Absolutely critical.
Yeah.
If you're only going to search once or twice, spending time sorting might take way longer than just doing a simple linear scan. The setup cost has to be amortized over many searches to be worthwhile.
That's a key point for remembering when to use what. Finally, the table looks at data orderliness. Does the method care if the data is sorted?
Linear search doesn't care. Hash search doesn't care either. It works on unordered data just fine. But binary search requires the data to be sorted. That's its fundamental requirement. And tree search, specifically binary search trees, relies on the data having some kind of orderable property so you can make that left-right decision at each node.
Okay, that comparison table is incredibly clarifying. It really lays out the strengths and weaknesses.
No.
So now we have this information. How do we apply it? The source gives some scenarios, right? Based on data size, speed needs, update frequency.
Exactly. It helps you map those table characteristics onto real-world problems. You need to weigh those factors for your specific case.
So when would you actually choose good old linear search, given its slowness?
Well, linear search shines when versatility is paramount. You don't want to, or maybe you can't, do any pre-processing. Maybe the data format just doesn't allow easy sorting or hashing.
Okay.
It's also, as we just discussed, a totally valid choice if you only plan to query the data once or maybe just a handful of times. The pre-processing time for the faster methods would just swamp the actual search time savings.
Right. Total time matters.
It's also perfectly fine for small data sets. If n is small, is fast enough, and critically, it's often the best choice if the data changes very frequently. Lots of insertions and deletions. Why? Because there's no complex structure like a sorted array or a balanced tree or a hash table to constantly maintain and update. You just add or remove from the list.
Okay. Simple, flexible, good for small data, one-off searches, or super dynamic data where setup maintenance is just too much hassle. Makes sense. What about binary search?
Binary search is your go-to for larger volumes of data where you need reliable, fast search performance. But it's typically used on arrays. Arrays need a contiguous block of memory. So while it handles large data well, it might struggle with truly massive data sets that won't fit in one consecutive memory chunk.
Ah, the contiguous memory limitation.
Exactly. And the huge caveat we saw. It's terrible for data that has frequent additions or deletions. That cost to maintain the sorted array by shifting elements is often prohibitive. So you use binary search when you have a large, relatively stable, sorted array and need fast lookups. Think maybe a dictionary loaded into memory that doesn't change often.
Got it. Efficient search on stable, sorted blocks. What about the speed demon, hash search? When is the right call?
Hash search is ideal when that absolute fastest query performance is the #1 priority. You need near-instant lookups for specific items, checking if an element exists in a set, looking up a value by its key in a map or dictionary that's hash table territory.
Okay, but the downsides?
Big ones. It's not suitable if you need the data to be ordered or if you need to perform range searches, like find all items between X and Y. Hash tables scramble the order based on the hash function.
Right, order's lost.
Also, its performance, while average, really hinges on a good hash function and effective collision handling. A bad hash function can lead to lots of items hashing to the same spot, and performance can degrade significantly, even towards a worst case. You need to be mindful of that.
So potential performance pitfalls.
And remember the space cost. Extra space for the table itself, which can be an issue for very large data sets, plus the time to build it initially. So use it when you need blazing fast lookups of specific items. Order doesn't matter. You have the extra space, and you're confident in your hashing strategy.
Okay. Super fast for exact matches if order is irrelevant and you handle collisions well. Finally, tree search. Where does it fit?
Tree search, especially using things like balanced trees, is really suitable for massive data sets. Much larger, perhaps, than what fits comfortably in a contiguous array for binary search, because tree nodes can be allocated anywhere in memory and linked by pointers.
So better for really huge data than array-based binary search.
Often, yes. And unlike hash tables, trees naturally maintain the order of the data. This makes them great not just for finding specific items, but also for performing range searches efficiently. You can easily find all items within a certain range by traversing the relevant part of the tree.
Ah, so order and range queries are strengths here. Any catches?
Well, the source mentions the risk with a simple binary search tree, BST. If you insert data in a sorted or near-sorted way, the tree can become very unbalanced, essentially degenerating into a linked list.
And then search becomes.
Back to n. You lose the whole logarithmic advantage. It behaves like linear search down a long, skinny branch.
Ouch. That's bad. How do you avoid that?
That's where self-balancing trees come in, like AVL trees or red-black trees, which the source mentions. They automatically perform rotations during insertions and deletions to ensure the tree stays reasonably balanced, guaranteeing that performance for search, insert, and delete.
Okay, so balancing is key for reliable tree performance.
But, as always, there's a small trade-off. Those balancing operations add a bit of complexity and overhead to the insertion and deletion process compared to a simple, potentially unbalanced BST.
Wow, okay. So many layers, so many trade-offs. It really drives home that there's no single best way. It's all about the context, isn't it?
It absolutely is. Understanding the data's characteristic size, how often it changes, whether order matters, and your operational needs, how fast search needs to be versus insert delete, how much memory you have, that's what guides the choice.
So, stepping back from the details, what's the big takeaway here? How does understanding all this help us, really remember it and use it effectively?
I think the core realization is that there's no free lunch in algorithm design, especially with search. You're constantly making trade-offs.
Like what?
Often it's simplicity versus speed. Linear search is simple but slow. Adaptive methods are fast but more complex and need setup.
Right, or space versus time.
Exactly. Hash tables and trees give you speed but cost extra memory space. Linear and binary search on arrays are specificity extra but might be slower or less flexible for updates.
And that pre-processing cost versus search speed.
That's a huge one. Is it worth spending time upfront, sorting or building a structure to make future searches faster? Only if you're going to do enough searches to recoup that initial investment.
And understanding these trade-offs isn't just for computer scientists, is it?
Not at all. It's fundamental. Whether you're actually writing code or maybe managing a database or honestly just figuring out how to organize your own files or notes,
Yeah.
you're making these kinds of choices implicitly.
Yeah. Do I spend time tagging all my photos now so I can find them easily later, or just dump them all in one folder and rely on scrolling?
Precisely. That's a linear search versus investing in a kind of metadata structure. This deep dive shows that this seemingly simple problem, finding something, has this incredibly rich landscape of solutions, each with its own niche, its own advantages and disadvantages. Knowing which tool to pick requires exactly this kind of deeper understanding of the nuances we've dug into from the source.
It really does provide a fantastic mental framework. Okay, so just to recap for everyone, making sure this sticks. We defined search algorithms, looked at the two main approaches, brute force traversal versus adaptive methods using structure. We detailed linear search, simple, no setup, binary search on sorted arrays, fast search, bad updates, hash search, average fastest lookup, need space, no order, and tree search, balanced, good for massive data, handles order and ranges. We compared their performance, space needs, and setup costs. And we saw how the right choice depends entirely on your specific scenario, data size, stability, order requirements, performance needs, all drawn from that clear analysis in the Hello Algo material.
Hopefully, that structured walkthrough helps cement the concepts for the long term.
That's absolutely the goal. And, thinking about all these different strategies, the straightforward linear scan, the clever divide and conquer of binary search, the almost magical direct jump of hash search, the carefully structured path of tree search.
Yeah.
It makes you think, doesn't it? What does this variety tell us about problem solving more broadly? Sometimes, maybe the simplest brute force way is the best, precisely because it needs no special setup or conditions. But so often, investing that effort up front, doing the pre-processing, organizing the information, leads to these incredible, almost disproportionate gains in efficiency down the line.
That's a great point. The prep work pays dividends.
It really is this fundamental balancing act, isn't it? Between putting in the work now for future speed and ease versus just dealing with things as they come. We see it in algorithms and, well, pretty much everywhere else, too. The messy desk versus the perfectly filed cabinet.
The context always dictates the best strategy. It's a powerful parallel.
Definitely something to chew on. A great place to leave it for this deep dive. Keep exploring, keep asking why, and keep thinking about how to find things efficiently.